All right, so in our last video, we looked at measuring angles using degrees, which again, that's should be pretty familiar for just about everybody. But what's probably not familiar to a lot of people is measuring angles using a radian, or the units called radians. And even though this is probably unfamiliar, we don't use it that much kind of in common language, I guess. It's extremely important in math and calculus in particular. In fact, in calculus, once you get to calculus, we basically throw out the idea of degrees completely, and we favor radians anytime we're measuring an angle, and there's very good reasons for that, which you'll learn about when you get there. But for now, we just want to introduce the concept. So what is a radian? Remember, a radian is just another unit that we use for measuring angles, kind of like how you can measure distance using a lot of different units. Distance can be measured in meters, it can be measured in feet, miles, kilometers, all sorts of different units of measure, but they're all measuring the same thing. So a radian is not measuring anything different than degrees are measuring. It's just a different unit. But how do we define this unit? So if you imagine the angle that we're measuring as living inside of a circle. So the initial side and the terminal side can both be thought of as radii for a circle. And if we were to, let's just say the circle has a radius of r. If this is my initial side and this is my terminal side, if the angle, which is labeled a t here, if the angle that this creates sweeps out an arc of a circle, so we call this an arc, this little segment of the circumference of the circle. If it sweeps out an arc such that the length of that arc is equal to the radius, this is an r and this is an r, then we call that angle 1 radian. So this is 1 radian right here. 1 radian. Now that might seem like a really bizarre way to define an angle, but if you think about it for a minute, what that does is it creates a direct relationship between the angle that we're measuring and the arc that's subtended by that angle, the arc that's swept out by that angle. And this is really important because, as we're going to see it towards the end of this section, that relationship between the angle and the arc of the circle that it sweeps out allows us to come up with some really useful formulas for things that are used in a number of applications. So let's move down to an example here, because what we've talked about here is just what 1 radian looks like. But it's helpful to come up with some familiar values for radian measure. For example, we know that a full circle in degrees is 360 degrees. This is clearly not a full circle. 1 radian is just a piece of a circle. So how many radians are there in a full circle? Is there a way of determining that easily? Well, let's think about that. If I have a full circle like this, okay, and I've swept out the arc corresponding to that full circular rotation, that would be the same thing as the circumference of that circle. Whoops. I have to remember to move the page up. So here's the circle that I just drew. That arc is the circumference of the circle, which we know if a circle has a radius of r, then the circumference of a circle is 2 pi r. Okay? So with that said, there's a direct relationship between the angle that's swept out and that circumference, and we define 1 radian to be equal to the arc that has the same length as our radius. Now what this does is it creates a proportional relationship that we can use to determine different angles using radian measure. So what I want to do is create a proportion, and again, 1 radian corresponds to an arc length of r. Okay, so I put the radian measure for my angle in the numerator of this ratio, and I put the length of the arc in the denominator. Proportions are a statement of equality between two ratios. So now what I want to do is put the radian measure of a full circle, which we don't know. Remember, that's what we're trying to find. I'm just going to call that theta. Remember, we commonly use theta for unknown angles. And divide that by the arc length of the arc that's swept out by that full circle. Well, again, the arc length is the circumference of the circle in this case, so that's 2 pi r. Okay, now we solve proportions using cross multiplication. So if I'm solving for theta, remember it's theta that we want, that's the angle that we're talking about. Then I have theta times r, theta r, equals 1 times 2 pi r, that's 2 pi r. Or solving for theta, I can divide both sides by r, giving me theta equals 2 pi. So a full circle in radian measure is 2 pi. Now sometimes we write 2 pi rad being short for radians, but more commonly we don't write anything, because usually it's clear from context that we're talking about an angle, and excluding the units implies that we're talking about radians. Degrees will always have that little circle indicating that you're using degrees for your units. Okay, so this is what a full circle looks like in radians. Get used to that number, 2 pi. What then would be a half circle? Well, I don't need to go and create a new proportion to solve for that. If a full circle is 2 pi radians, then a half circle should be exactly half of that. Half circle would be half of 2 pi, which is just pi. Notice this time I'm not writing the rad. I don't really need it. It's clear that I'm talking about radians. Okay, so this little picture down here, this image kind of shows you some different radian measures in a full circle. And you're going to notice that most of the time when we're dealing with radians, we usually won't just be talking about 1 radian or 2 radians or 5 radians or 4 radians. Even though those exist, more often than not, we're going to see pi showing up in our radian measure for different angles. And that's because, again, most of the angles that we are going to be using in this class are subdivisions of a full circle. We're dividing 2 pi by some whole number, which is going to look like a fraction usually involving a pi, or just some multiple of pi. Okay, so here you're seeing the full revolution is equal to 2 pi radians, but here's what 1, 2, 3, 4, 5, 6 radians would look like. By the way, pi is 3.14 when you round it. You know, it's not actually 3.14. Pi is an irrational number, so its decimal representation doesn't terminate, it goes on forever, but it's commonly rounded as 3.14, which means 2 pi would be approximately 6.28. What that means is that a full circle is just a little bit more than 6 radians, approximately 6.28 radians, but we can write 2 pi for accuracy. All right. Now, in that previous example, we worked out the radian measure of a full circle as well as a half circle. And we saw that it was easy to find the half circle just by cutting a full circle in half. So we went from 2 pi down to pi. But what about finding other angles in radian measure? In fact, what we're going to be doing a lot of in this section is converting between these two systems of measurement. So in other words, if you have an angle that's been measured in degrees, how do you convert that angle into radians? And vice versa, if you have an angle that's been measured in radians, how do you convert that into degrees? So the proportion here is what we're going to be using essentially as our formula for that. And what we're doing is we're creating one ratio for degrees, one ratio for radians, and we're using the 180 here and the pi here as sort of like our set values for degrees and radians. So in other words, I know that 180 degrees and pi radians both represent a half circle. So 180 degrees and pi radians represent the same angle. Which, if this proportion is to be true, whatever angle we're looking at in degrees can go here, and its counterpart in radians can go here, making this equation true, this proportion true. Okay, so let me illustrate how I would use this. I want to convert a 90-degree angle from degrees into radians. Now there's a couple ways you can do this. We don't need to use that proportion because we already know that a 90-degree angle is a quarter of a circle. So you could take 2 pi, which is a full circle in radians, and divide that by 4. That should give us the correct answer. But I want to practice using this proportion method. So the theta d here represents the angle that we are looking at in degrees. We already know what that's equal to, so that's 90 degrees. And I put that over 180. Okay, equals theta r. This I don't know, but that's the value I'm looking for. What is the radian measure of that angle? And I put that over pi. Okay, and I can solve this using cross multiplication. However, it's usually easier to simplify this fraction first to make the work a little bit easier. 90 over 180 simplifies to 1/2, so this becomes 1/2 equals theta r over pi. Now, I'm not even going to think of the next step as cross multiplication, even though I could. I'm trying to get the theta r by itself, and that would be easily done by multiplying both sides by pi to cancel that pi out. That would give me pi over 2. Okay, so that would be the radian measure corresponding to 90 degrees. A 90-degree angle is the same thing as a pi over 2 radian angle. Let's try this again with a different degree measure. Notice this, in this case, the degrees, or the angle is measured using a negative value. So all that means is that the angle would be measured clockwise as opposed to counterclockwise. Since we're not sketching the angle, that's not that important. But we can't ignore it because this is going to tell us that our radian measure also has to be negative. So same approach, negative 250 over 180. Set that equal to theta r over pi. Now same idea, I'd like to simplify this first, and I notice that I can divide my numerator and denominator by 10, giving me negative 25/18 equals theta r over pi. That doesn't get any simpler than that, so I can just multiply both sides by pi again to solve for theta r. Negative 25 pi over 18 equals theta r. Okay. Before I move on to the next example, I just want to point something out. You'll notice that my answers in both of these cases came out to fractions involving a pi. A lot of people have some reluctance when working with fractions, have some difficulty working with them for one reason or another. This is the class where that's going to cause you a lot of problems if you have difficulties working with fractions. In trigonometry, there are fractions all over the place. If you're not comfortable, like really comfortable working with them by now, you have to get comfortable. Or this class is going to be very, very difficult. So those of you who are in my support class, that's something that we're going to work on. We're going to work on improving our skills working with fractions. But I recommend brushing up if you feel a little rusty on that. One more, 900 degrees. So 900 degrees, there's really nothing new in this example. It's the same exact idea. So 900 over 180 equals theta r over pi. Now 180 actually goes into 900 evenly, so I can just treat this like division. That comes out to 5. I get 5 equals theta r over pi. And then multiplying both sides by pi, I get 5 pi equals theta r. Now that one we can actually visualize fairly easily because, again, remember 2 pi is one full revolution, one full rotation around that circle. That means 4 pi, if you double 2 pi, would be 2 full rotations. So I can think of 5 pi as 4 pi plus another pi. And what that would represent is 2 full rotations plus another half rotation. So not hard to visualize that when we get multiples of pi like that. Okay, let's practice doing this the other direction. So this time we have angles that are given to us in radians, and we want to find the degree measure for these angles. Now this first one, notice 5 pi. I could use my proportions, my proportion method to solve this, but one thing that you want to take advantage of in math is using past results that you've already done the work for. I believe the phrase is work smarter, not harder. So over here, we found that a 900 degree angle is equivalent to a 5 pi radian angle. Well, there's 5 pi. Without doing any work, I know that the degree measure that corresponds to that is 900 degrees. No, it's not cheating if I already did the work somewhere else. So that's it, 900 degrees. 7 pi over 6, we don't know that one yet. We haven't dealt with that one yet. So let's try and solve that. So this time, going back to my proportion, we have theta r this time. We know the radian measure of our angle. What we don't know yet is theta d. So that's what I'm going to be solving for in this one. Theta d over 180 equals 7 pi over 6 over pi. Okay, and again, this is where it really pays to be comfortable working with fractions. So first thing I notice is that the pi's will cancel out. That means I have theta d over 180 equals 7/6. Okay. The next thing I want to do is multiply both sides by 180. So theta d is equal to 7/6 times 180. And again, if you're comfortable working with fractions, you don't need a calculator for that. It's 210. Okay, 210 degrees. Now, thinking about that for a moment, it's helpful to have a way of sort of gauging if your answer is a reasonable one. In other words, we want to be able to look at a number, and if we're way off, if we totally messed up the problem, we want to be able to know that just by looking at the number. We want to be able to think that's not a reasonable answer to get. Is 210 degrees a reasonable answer to get? Well, notice that 7 pi over 6 is just a little bit more than half a circle. And how do I know that? Well, pi radians would be a half circle. But pi radians is the same thing as 6 pi over 6, because that would simplify to pi. That means 7 pi over 6 is just a little bit more than pi, a little bit more than a half circle, or in degrees, a little bit more than 180 degrees. 210 is a little bit more than 180 degrees, so that feels like a reasonable answer to get. Okay, one more to go. A negative angle this time, so we're working with negative 22 pi over 9, and again, that's radians. Same exact thing, I set up a proportion. Theta d over 180 equals negative 22 pi over 9 over pi. And again, this will happen all the time with radians. If your radian measure has a pi in it the way that these do, oftentimes you're going to see that cancellation. So really, this is theta d over 180, and that's equal to negative 22 over 9. Okay, and then once again, we're going to multiply both sides by 180 and simplify. So let's see, what would that be? That's going to be 180 divided by 9, which is going to be 20 times that's going to be theta d equals negative 440 degrees. Okay. Now that one, again, if you want to think of this in terms of what a reasonable answer would be, negative, so it should have been negative, but ignoring the negative, let's just think of it as 22 pi over 9 radians and 440 degrees. So 440 degrees is more than 360 degrees, so it's more than one full revolution around a circle. Is the same true of this? Well, pi, or 2 pi, is one full revolution, but 2 pi is the same thing as 18 pi over 9. That's what would simplify to 2 pi. So that means 22 pi over 9 would be greater than that. So that's more than one revolution, just like what we're seeing here. So again, it's helpful to have those little tricks to sort of see, does my answer make sense, or should I go back and look for a mistake somewhere? Okay. I wanted to show you this little image down here. We'll stop this video with this last little example, or this last little explanation. This is probably very small to see, but we're going to look at this in much more depth a little bit later in chapter 7. There's a certain set of angles that we sort of single out in trigonometry because they have some nice properties that make them easy to work with. Those special angles are all indicated here. I'm not going to read them all off, but we have worked with some of them. So notice 0 degrees, 30, 45, 60, 90, and then you know, the rest of them are all written here, along with their radian measures. We're going to investigate those in much more depth, not in this section, but later in chapter 7. So there they are just for reference. Okay, that's going to be it for this video. We'll pick up where we left off in the next one.